Hey guys, welcome back to chapter 12. In this video, we are going to talk about a different way to calculate Gibbs free energy. This is going to look very similar to something that we did with entropy earlier in this semester. So we can use standards and look at a chemical reaction, products minus reactants. So the standard that we're going to use is something called standard free energy of formation. Standard free energy of formation is the change in free energy when 1 mole of a compound forms from its constituent elements in their standard states. Right? So we have water, for example, and the elemental forms are hydrogen and oxygen. When hydrogen and oxygen come together to form the compound, there is free energy released. Standard free energy is whatever that value is, okay? Based on standard states, so 1 mole, room temperature, 1 atm, all of those things stay standard. When we look at the Gibbs free energy for a reaction, so we're going to look at this change in Gibbs free energy for a particular reaction, and we're going to use these standards. And just like we looked at entropy, it's going to be the change in Gibbs free energy for the products minus the change in Gibbs free energy for the reactants. So final minus initial, or products minus reactants. And then we don't want to look at just one product, one reactant. We want to look at all of them. So there's going to be a summation piece to this. And then the last piece is, again, we need to acknowledge how many moles of each of these we're making. So number of moles of the product, summation for the reactants, number of moles for the reactant, right? So we're going to take each of the products, moles times standard, add all those together. Each of the reactants, mole times standard, add all those together. And then we're going to subtract products minus reactants. So here's the kind of official formula. I think these formulas are a little bit messier than they need to be. So we're just going to kind of hash out an example. And I think that's the easiest way to learn these. So here's our example. We want to calculate the standard Gibbs free energy for the following reaction. So we got methane reacts with oxygen to produce carbon dioxide, water, and ozone. We are going to look at the standards for each of these. One thing to point out is if something is in its elemental form, we don't get any energy released because that's just how it exists. So the energy for its standard form is just 0. But anything else is going to have some sort of energy associated with it, whether it's releasing or it is absorbing. There's going to be some sort of energy associated. All right, so we're going to dive into this problem. I always like to do the products first because that's just a good reminder for me that it's products minus reactants. So on the next slide, I'm going to do the entropy change for the products. So for the products, the first I'm going to look at is carbon dioxide. So carbon dioxide is negative 394.4 kilojoules per mole. So we're going to take 394.4 kilojoules per mole. Then we have to take into account how many moles we're making, and we're making 1. We multiply that by 1 mole. Now I'm going to add that to the other 2 products. So the next one is water. So water is negative 228.6. kilojoules per mole. And then we have to take into account how many moles we're making. So we're producing 2 moles in this chemical reaction. So this is the value for 1 mole, but we're making 2. Let's multiply by 2. And then lastly, we're going to add that to ozone. So ozone has a positive, so it's positive 163.2. And we have to take into account how many moles we're making. So we're making 4 moles of that. And again, moles cancel. All right, so I'm just going to clean up this equation. So negative 394.4 times 1 is just negative 394.4. Moles canceled, so we're left with the unit of kilojoules. Now we're going to add that to negative 228.6 times 2. And this value is negative 457.2. And again, the unit is kilojoules. Then we're going to add that to 163.2 times 4. And we get 652.8 kilojoules. So then I'm going to add those all together. So negative 394.4 plus negative 457.2 plus 652.8. And we get a value of negative 198.8 kilojoules. So that's the the Gibbs free energy change for the products. We're going to do this same process, but we're going to do it for the reactant. So why don't you guys go ahead and pause the video and see if you can determine the Gibbs free energy change for the reactant. All right, so now I'm going to walk you through it. Hopefully you've got it finished. Reactants, we're going to have first methane. So we've got CH4. The Gibbs free energy for that is negative 50.5. Kilojoules per mole. Then we have to take into account how many moles we're making. And we're only making 1. So times 1 mole. And then we're going to add that to our other reactant. So our other reactant is oxygen, and that has a Gibbs free energy of 0 because that's how it exists in its elemental form. But for completeness sake, I'm going to go ahead and say 0 kilojoules per mole. And then take into account that we're making 8 moles, or using 8 moles. All right, so 0 times 8, that just kind of drops out. Negative 50.5 kilojoules per mole. Moles on top, moles on bottom cancel. So the Gibbs free energy change for the reactants is just negative 50.5. Now, to finish this problem, we don't want to know what each of those are. We want to know what is the Gibbs free energy change for the reaction. So we're going to take the products minus the reactants. So we've got products are negative 198.8 kilojoules minus reactants are negative 50.5 kilojoules. So plug that into our calculator, and we get the Gibbs free energy change for the reaction is negative 198.8 minus negative 50.5, and we get a negative 148.3. Now we have to ask ourselves, does this make sense? What does that mean, and does it make sense? Okay. So our Gibbs free energy value is a negative value. So first and foremost, what does that tell us? Spontaneous or non-spontaneous? Yeah, it's spontaneous, right? So this is a reaction that's going to spontaneously happen. Let's go back and ask ourselves if that makes sense. So we know there's kind of two things at play here. There's enthalpy. We don't really have any information about the enthalpy. Is it exothermic? Is it endothermic? But if I look at entropy, right, everything is staying kind of in the gas form, so not a lot of information there. So this is a spontaneous reaction at 25 degrees Celsius, and that's all that we really can deduce from that information. I hope you guys found this helpful.